even at the very top, at the level of the leadership in the AI community, there are very split visions in terms of where it's all going. On the one perspective, you have these gloom and doom situations of AI completely replacing jobs, completely transforming the economy. And on the other hand, you have other people that say AI's transformative potential depends on a whole lot more factors than we can envision at this point in time, and it's actually not going to get there without some significant effort. And it's just wide variance of opinions that we have that gives a lot of people the sense of, if the experts can't agree on what's going on, then how should we know, for example, where should we invest? What techniques should we be looking into? How do we make sure that what we're going to work on today isn't outdated in a year's time? So it's a very difficult landscape to navigate for sure.
ARM is the industry's highest performing and most power efficient compute platform with unmatched scale that touches 100% of the connected global population. Together with the world's largest computing ecosystem and 22 million software developers, ARM is building the future of AI. Hi, my name is Junko Yoshida. I'm the editor-in-chief of Junko's Talk to Us. This is the special domain-specific AI series that we have been working on. And today we are focusing on the automotive segment. And with me is Ron Wilson. He's focused on the technology side of the business. And today's guest is Mauricio Munoz. He is the senior research engineer at AI Sweden. Hi, Mauricio.
Hi, Junko. Hi. Thanks for having me.
Well, thanks for coming. I met Mauricio only a month ago at the MIT's Advanced Vehicle Technology Consortium's meeting. During that speech, you really focused on AI, but you actually did focus on domain-specific AI, the need for domain-specific tools for applications such as automotive. Before I dive into that, Mauricio, I want you to introduce yourself because you have a very interesting background. You are not only just a researcher, but you have actually traveled different parts of the world to become who you are today, right?
That's right. That's right. So my career has taken me to some interesting places, I have to say. So yes, I'm Mauricio, as you've said. My background is in computer science. I'm originally from Quito, Ecuador, and I did essentially my bachelor's and master's in Germany. And as part of my graduate study, I actually spent some time at MIT doing my thesis, my master's thesis, together with Brian, who we met at the AVT consortium meeting. And after that, this is where I jumped into industry, and automotive was really the first place where I started looking. And I ended up in England, of all places, working for Jaguar Land Rover in their research department. So I did a bit of computer vision research there and just general machine learning engineering in their research department there. And then I very quickly also, as part of my time there, worked on a very interesting project, which was the America's Cup. I didn't know anything about sailing before then, so that was really new to me. But the more that I got into it, I was really just fascinated by how incredibly technical and interesting of a place it is to do some proper research work, and machine learning was really up and coming topic at that point in time. Obviously, in a much earlier phase than it was today, but essentially my role there was to take a look at all of the data that was coming off of the boats and try to analyze it to try to make better design decisions in terms of how you configure the boat for sailing. So I spent about 2 years there working as a machine learning performance engineer. And then after that, I actually moved back to Germany, where I spent some time at Bosch, at the Bosch Center for Artificial Intelligence, because I decided that actually machine learning research is really where the future is at. And I dedicated 7 years of my life to that place and to the group there. with a very strong focus on deep learning and computer vision, with a whole set of very varied industrial applications, from automotive to healthcare to embedded AI to manufacturing to everything.
Wow.
And then my most recent position, as you've just mentioned, is senior research engineer at AI Sweden. AI Sweden is Sweden's national AI laboratory. We do a mix of applied and fundamental research in AI, everything from topics on also automotive is one of the things that we do, but then also topics related to AI security, which is of course at the moment gaining a lot of interest from the international community. I guess for all of my career, I've been to some extent involved in machine learning AI research, and that's, I guess, my my profile is yeah, what that looks like.
I think it's actually very fitting because AI has been sort of has this really steep trajectory over the last few years. But at the same time, this begs the question, because every time when people talk about AI, it becomes like AI is there to solve all our problems. And that is not exactly, I think the one thing actually glom onto when you started to talk about AI, you talk about cognitive dissonance related to everything that actually we face in the society today, right?
Yeah, exactly. It claims that you hear time and time again from, I guess, people and figures that pose themselves as visionaries. Obviously, a lot of them have very strong careers to also back that up. And so that's, I think, also where a lot of this cognitive dissonance is coming from, is because even at the very top, at the level of the leadership in the AI community, there are very split visions in terms of where it's all going. On the one perspective, you have sort of like these gloom and doom situations of AI taking over or otherwise, completely replacing jobs, completely transforming the economy. And on the other hand, you have other people that say, actually, AI's transformative potential depends on a whole lot more factors than we can envision at this point in time, and it's actually not going to get there without some significant effort. So there's a lot more realist, I would say, from my point of view, a lot more sobering perspectives. And it's just wide variance of opinions that we have that gives a lot of people the sense of, if the experts can't agree on what's going on, then how should we know, for example, where should we invest? What techniques should we be looking into? How do we make sure that what we're going to work on today isn't outdated in a year's time? So it's a very difficult landscape to navigate for sure. Yeah.
Yeah.
Mauricio, it seems like perhaps part of that dissonance is the difference in perspective between the generalists and the domain-specific folks, where in the general case, if something is approximately useful, it's great. In a deeply embedded application, if it makes any errors at all, it's catastrophic. Is part of it just a difference in perspective?
I think absolutely it comes down to also that. I mean, on the one perspective, you have academics that are, I guess, enamored by this concept of generalization, right? So basically training a model that can, with some closed data set, and then you figure out, oh, this works in areas that perhaps it wasn't intended to sort of like work in, and gives you reasonable responses in situations that perhaps weren't completely inside of the training data. And that's, I guess, ultimately the holy grail of machine learning and AI. And we've seen a lot of evidence for that over the past couple of years. So I don't want to dismiss the claims that it's, that we won't get there, right? That we won't make it useful. And I can certainly understand the enthusiasm, right, of these journalist approaches of saying, hey, we have something of value here. But at the same time, you have to remember that, of course, adopting this and actually turning it into something that exists in a product at scale, and in particular with the safety guarantees that any piece of technology is supposed to or should provide its consumers, is a completely different challenge in a way. In my perspective, a much more difficult challenge. And as I said before, the validation and verification of machine learning has, fallen quite a bit behind what we can now do state of the art wise. So you have like this gap that, we somehow need to close. It's in a sense two different worlds that we're still trying to bridge. And I don't have the answer to that. I don't think anyone really has. But yeah, the difficulty is certainly there.
Yeah. The one of the things actually that struck me is that I think this gap, you just touched upon the gap between the general AI tools that people are excited about and the actual useful tools that automotive engineers would like to use to close that gap. Now, does that require for the automotive industry to design its own AI models that are not created by OpenAI or the Microsoft or those, big guns out there? I mean, how does that work? Who is going to actually close the gap?
That's a really good question, and the answer to that question, in my opinion, is precisely the domain experts. So, and this answer is motivated by essentially the distribution of data that we see in the real world, right? So, if you take a look at how these generalist models are trained, I mean, they're basically web crawling everything that is available out there that is sort of like quote unquote open source. Although, I mean, big caveat here that we can, or disclaimer that we can address later, but they're basically getting everything that's available and training models based off of that. But the data that, for example, automotive companies have in terms of new sensors that are perhaps not yet on the market, right, that they really want to develop the models for, right? I mean, these data aren't available freely on the internet, right? So what you're getting out of these generalist models is really a very small percentage of the full capability of what you could actually get if you were to train on the whole set of data that's available everywhere. And so I think the challenge is more on the domain experts because they're sitting on the gold mine, essentially, right? That's what it comes down to, right? I mean, if we've basically learned anything from the past 5 years in AI development is, I mean, not even learned, but even just remembered, right? Garbage in, garbage out, right? A lot of the effort that goes into training these very large models nowadays has to do with actually just pre-filtering garbage data out of the learning process and to make sure that you inject high quality data. And all of the studies that we have today indicate that the value really is in using the high quality data. And that, as said, is what probably is sitting inside of these automotive companies. So we need to have the expertise to be able to leverage that. The first challenge that you have as an enterprise, for example, inside automotive, to make AI work for you, it isn't a technical one. It's not about training the models or developing the techniques. I mean, these are out there. We have really incredible open source alternatives that you can already leverage to a very large extent, right? And that's certainly not the full solution, but still, that's there for you to use, right? So it's really not the technical. It's more the organizational aspects of making sure that your organization is in a position to really assimilate the fast pace of AI development. And that's also why I really like the concept of consortia, right? Because here you're potentially sharing data between different partners and making sure that all this valuable gold, right, isn't sitting behind a single silo and not being ever used, but it's actually coming together into an even more valuable stockpile that you can use to basically solve common problems that everybody in the automotive industry has. I think it's quite clear to everyone there are problems that everybody needs to contribute to, not just on a very individual enterprise or company basis, right?
Setting aside for a second the question of would two automotive companies ever actually share data, is the data specific to the particular sensor configurations on which it was collected? So, for instance, it would be very hard for a company that uses LiDAR heavily to share data with a company that's entirely video camera specific?
Yes. Yes, the short answer to that question is yes. Your models won't be able to generalize between different data modalities. I think that's quite a jump. You need to show it a little bit of, what do you mean when you say radar? What do you mean when you say LiDAR? Because of course they give you different different value, right? I mean, there is a reason why there has been investment, for example, LiDAR technologies over just video, for example, right? They give you different facets of the same picture, and you want to basically build all these facets together to really make accurate predictions, right? That's the ultimate goal. The information they provide you isn't exactly overlapping, but yeah, and of course, I mean, one other thing that's worth mentioning is that, for example, one of the things that we at AI Sweden have been focusing on quite a bit in the last couple of years is we've recognized this challenge of sharing data is hard, right? There are legal limitations as to why you might not be able to do this. Aside from just like the technical or organizational factors. And there are techniques that allow you to essentially get around this in a sense, right? So instead of moving your data to where the model is, you want to move your model to where the data is, and then train individually inside of each silo, and then aggregate that information back to a global model. And this concept of decentralized learning, or also known as federated learning, we've seen a lot of success with this in the past, and really a really interesting topic that for sure will dominate the discussion in the coming years, as we figure out, hey, the amount of publicly available data is just, we've already trained on everything. So what else is there to train on? How can we expect the models to improve? And that's precisely this concept of, okay, we'll bring your model to where your data is, and then without your data ever leaving your silo, we can train there and then just get the insights, basically the learnings from the model, and get them back.
By insights, do you mean that you're training, the model is producing kind of a virtual world or a symbolic representation of the data it was given, and then passing that to another model that works on that representation?
Yeah, in a sense, you could think of it that way. I guess the more general approach would be, we're learning, basically using that data to generate a learning signal, right? What we didn't know in the industry is sort of like gradients, right? So you can take these gradients, or you can take even just the updated model, right? You can take a global model, move it to some data silo where the data never leaves, train the model a little bit there, and then you get the resulting model. You get that model back in its entirety, and then you fuse that new model with the original old model, or with other models coming from other data silos. So it's insights, I guess, mostly on an abstract term, but I think, as you say, this will go more and more towards in the direction of actually simulating things and simulating environments, something that's more complicated, I guess, and more in depth than just learning a very simple learning signal from that data. Yeah.
So what you just talked about, actually, there are two things that I want to discuss, because in your speech, you talked about, you had an estimate, maybe 20% of the data out on the internet is crawlable, versus 80% are locked in the private server. That's where does that data come from?
That is actually from an Intel report that I read, but it really, in a sense, also makes a lot of sense. I mean, I've, as said, also worked inside of these OEMs, so I know the sort of like vastness of the data lakes that they have, and it's quite a bit of an impossible challenge, to be honest, to basically sort through it all. So yeah, it's whether the numbers are exactly on point, I mean, I don't know, but I guess the gist really is, there's a lot of valuable things sitting in data silos that nobody has access to. Yeah.
So one of the model you just talked about, bringing my model to somewhere that is where the data is that something that on the research level things people are doing? Because I haven't really heard that like Tesla or Waymo are doing anything like that at this point in time, right?
Yeah, so actually it's very much a research topic for sure, but it's also a very practical one. So if you've ever really used something like Gemini, for example, this the large language model from Google, this was trained in a distributed sense, basically, like I've explained, not because of the data privacy aspect, but because of the energy concerns. And if you recall from my talk, that was one of the points that I also wanted to drive home. It's basically saying, you can't concentrate all this compute power in a single data center, because you'll bring down the entire power grid. And so you have to distribute these compute centers geographically across, for example, the United States, and learn in this distributed fashion. So actually, it's not just a research topic, it's actually a very real one. It's something very concrete that we experience, even though we don't know about it, essentially. Yeah.
I guess to me, the concept of distributed training raises the concept of security. How do you protect the model from the remote site where you're doing training on it? And maybe more profoundly, how do you protect the model from bad actors?
Absolutely. As soon as you go into this distributed mode, then you're, of course, vulnerable to things like data poisoning, right? So what happens if a bad actor gives you poisoned data, right, that you can somehow use to, for example, include backdoors? If you're training a language model, right, you can later prompt it using your backdoor and then have it do whatever it is you want it to. And these are all very, very serious security concerns. And also is that one of the reasons why AI students really focusing on AI security right now, more than probably any other topic, is precisely because of things like this. And the other aspect that comes along is that, if you've trained your model in this way, then what guarantees do you actually have that your model, for example, doesn't leak information? I mean, there's been research work that basically shows that even though the data is never moved across these silos, that it's still relatively straightforward, I would say, to have the model that's been trained as a result of this decentralized training, to have it reproduce some of the data samples that you precisely don't want to get out, right? And these are all a bit of on the vanguard of research, I would say, at the moment. But absolutely, I mean, this is where AI security and security for AI, these the two sides of the same coin, I would say, really come into the focus, and also one of the reasons why I said we're really focusing on this topic at the moment.
Are we in another situation like we saw with financial technology, where the concerns about security lag about a decade behind the applications that create the risks?
I think so. I think so. I mean, I think it's very much the same situation as, I mean, I mentioned before, verification, validation of machine learning models, right? How can you guarantee that your model isn't going to predict something crazy or just do something completely unexpected? I mean, same problem that we have nowadays with hallucinations and large language models. Like what sort of like theoretical guarantees can you provide me? And the real answer to that is, very, very little guarantees at all, right? And it's the same aspect with the security things. I think, particularly in the US, I would say there's this mindset of self-regulation, right? In the big companies, where it's the companies that are deciding, okay, we have this product, we could make essentially a lot of money doing this, or we could, it could be to our advantage to bring this on the market, but we don't have all the solutions for how to regulate it, how to, providing the safety measures for it. So we're just going to essentially do our best, right? But it's just like, it just comes down to the fact that we don't have a theoretical framework for this yet, right? I mean, it doesn't exist. I mean, what we have is a product of our empirical studies, of our empirical work, of essentially just throwing more and more data and scaling the models in terms of data and model size, and going, whoa, the things that we can get out of this are amazing. I mean, all these emergent properties that we see from these foundation models are absolutely amazing. But we don't really understand them, like what's going on behind the scenes. And what's funny is that, what I'll add to the discussion here is that while I was working at Bosch, one of my largest projects, where I spent 2 or 3 years on, actually, so about half the time that I was there, was on explainability for deep learning models. So how can you take a model, that black box thing, and have it explain its decisions to you, as in, like, why did you decide, if you have a classifier, why did you classify this as a pedestrian and not a bicycle rider? Because if your explanation is sound, then this is a good thing. If your explanation is not sound because of some introduced bias in the data set or something like this, then this is something that you want to know. And this was a really difficult task. In a sense, the research didn't progress much after a certain point. And moving on from that era to where we are now, it's quite clear that things have just gotten worse, in the sense that it's not just the models that are black boxes now, right? It's also the data, right? A lot of the data sets that these very large foundation models are being trained on, a lot of the technical reports that we get from the companies that train them don't say anything about the data. We have no idea what sort of statistics they were trained on, right? So the situation, I think, has gotten even worse in a sense. Definitely makes it for a very challenging landscape in this regard.
That's a very astute comment, because but from the layman's point of view, it is opposite. The things that the emergence of LLM suddenly make people feel confident that, as though AI, because AI can now speak and write, and it as though the AI is really understanding the situation, giving me the reason why it did it. But at the same time, AI can be gaming the system and trying to tell you that what you want to hear. So that's LLM actually broke through, but at the same time, with no safeguard with it, right? Yeah.
Exactly. And particularly language, I would say, I mean, there's a reason why we've had this explosion, right? In particularly with LLMs. And I mean, thinking a little bit more on the philosophical terms, I think it also has something to do with the fact that language is, to a very large extent, how we as humans transmit and communicate not only knowledge, but truth, right? So it's one thing to have, for example, a quote unquote dumb classifier machine learning model trying to basically tell you what it's doing via a set of classification decisions that you as a person have to interpret. It's a completely different thing if this same model can speak to you in natural language and try to essentially reason reason its thinking, right? Even though it may be based on completely false assumptions and biases that you don't want to have it in there, just the fact that it's communicated in natural language, I think for us as humans, there must be some biological component that is hardwired to somehow try to really interpret that at a more fundamental level. So I think this also explains why there's been such a meteoric rise in LLMs precisely for that reason. But yeah, it's a dangerous, it's a double-edged sword for sure. No question about it. Yeah.
So I'm thinking more of an application, automotive application level, that the AI kind of makes sense. Is really that using LLM and asking AI only to crawl if I am a auto company A, my company A's model, manual, so that I can look without looking up. I can ask the car that how do I change this windshield or something. That's kind of the most basic examples that I hear from automotive industry. Can you think of any other kind of useful AI applications specific to automotive that you can think of?
Yeah, for sure. So I could name a couple. So for example, from the user perspective, from the customer perspective, one of the things that we very quickly identified or I personally learned about while I was at JLR, for example, in the UK, was that your car is essentially a data center on wheels, right? In the sense that not only from the compute perspective and all the interesting things that are going on, but from the consumer facing side, there is such a complexity bottleneck in the sense that, your car offers 70, 80, 90 different functions, 99 of which you either completely deactivated or the user doesn't know about like at all that they exist because they're buried under so many menus and things like that. So to basically take your example just one step further, it's not about the user, that they know about how to do something, they have to figure out how to do it. That would be one example, like you've mentioned. The other would be to basically make this bottleneck as smooth as possible, in the sense of you design your interface in such a way that you minimize the number of clicks that you need to get to any number of functions that you want, right? And this should be a dynamic thing depending on user on how the user sort of reacts, right? So you have things like that on the user side. But I think the more interesting applications are actually on the engineering side of things, because if you take if you take a look under the hood at how automobiles are developed, right, it's there's a lot of legacy processes in there, right? Which to a large extent become quite inefficient, given, of course, the speed at which you can now do certain things. So I'll give you an example. Requirement documents, right, for engineers. So if you want to develop a new function, an ADAS function or something like that, then you have to look at all the safety documentation. You have to figure out, okay, this is the function that I want to implement in the car, and it should basically adhere to all of these prescribed safety requirements. And then also, these are the things that this function is really going to do. So the documentation of the function itself, how it integrates with the rest of the system. And so at the end, if you sort of like integrate a lot or, a couple of these functions, all of a sudden you have a very, very complex quote unquote manual for what your product really looks like. And this manual is a manual that isn't written by a single person. It's written by, myriads of people from across the company. And if you're really trying to get a grasp of, if I want to introduce a new function, what is this really, how is this really going to interact with the rest of the vehicle? What requirements do I really need to fulfill here? It's not a straightforward answer. Like writing these documents is really not straightforward. So the usage of LLMs to basically grasp all of this information and help you not only interpret requirements, but actually refactor requirements that might be written very poorly, that you could essentially write in a much more efficient way, and to basically just speed up the engineering process, right? So I think there's a lot of potential in that direction for sure. But then, I mean, to be completely honest, LLMs in particular, just as a basic vanilla LLM, I think is rather a very limited tool overall. So I think for automotive, you want, of course, much more interesting things, especially, as we, move slowly from the age of LLMs to, I guess, age of agents, if you will. So LLMs that have some sort of agency that can act in a predefined framework, that can take automatic actions depending on existing preconditions. I think that's going to be have a much more impactful role. But otherwise, I think there's quite a number of other tools that are out there that are more helpful to the automotive industry than just LLMs as they are right now.
Do you think we can take the LLM concept and apply it to driver assistance and autonomous driving, or are the tools that we've developed so far just going to be so much safer and so much more accurate?
So I guess it depends what you mean by LLM concept. If you're talking about getting these emergent properties, right, and using, I guess, using the value of really scaling in the data direction that you get, essentially making models better and generalize better because you're adding more data to them and training more data on them. I think there is going to be some use for that. I mean, we've certainly already, we can see it with, for example, vision models and computer vision, right? We have this to a large extent now. And a lot of it is also, of course, going on in the generative AI sphere, other from LLMs. So, for example, generation of synthetic data, right? So if you want to train your model on like different data modalities, so someplace where it's sunny, someplace where it's raining, where it's you have a lot of snow, and basically try to fill every possible gap of the entire data manifold, right, of everything, every possible condition, so that you can basically assess whether your model is going to do the right thing in unexpected conditions, right? So the synthetic generation side of things, from a computer vision perspective, I think we've come a long ways, right? And there's really amazing things that we can do with that now. But I think the fundamental problem is still not solved, in the sense that machine learning and AI are, by their very nature, probabilistic, right? This means that they can really only give you, a certain probability of doing the right thing, essentially, right? Whereas what you want as an engineer is you want a solid mechanical engineering guarantee that, by the laws of physics, this can't really happen, or a certain condition can't really happen. And this is what I was really advocating for in my talk, that actually, bringing in systems like LLMs together with things like symbolic reasoning systems, right? Or physics engines and things like that. So things that are grounded in very solid math, right? In very solid physics, or in very solid domain knowledge, something that you can go in and inspect as an engineer, right? And really know what's going on. I think it's going to be the interplay of these two things that is really going to push the industry forward, rather than just the ultimate reliance on scaling the next generation of GPTs or something like that, right? I think at the end of the day, we're always going to end up with this problem of, these things are probabilistic. The margin of error is shrinking, but it's never going to shrink enough so that you have this absolute safety guarantee that you can provide to users.
So the idea of just getting enough data to train an end-to-end model can work autonomously, it sounds like really depends on having physics-based and logical-based models working with it.
Yeah, so that's of course just my opinion. I mean, of course, you'll find people in industry that disagree, right? As much as, for example, you have people disagreeing on, is automated driving possible only with cameras, or do you really need other sensors, right? Like LiDAR and radar. I mean, we've had that discussion in the past, right? I think it's going to take more than all of that put together. And I think it's going to be this interplay between essentially what I call system of systems, right? It's not just an LLM as a system. It's not just a physics model as a system. It's basically modeling all of this as a joint system that's really going to push the bar forward. So
related to this is something I think you mentioned in your talk, Moravec's paradox.
Yes,
that models can be very good at very complex things and still totally fail at simple things, and it seems like more training doesn't make that converge on the simple things getting done too. But in automotive, it seems like it's the simple things that would be catastrophic if you failed at them. And nobody really cares whether you can figure out what typeface is used on the stop sign. They do care if you run over the stop sign. Is this
That's
a
exactly
fundamental
right.
thing that's just a principle of generative AI that isn't going away?
Yeah. I think so. I mean, I think we have enough experience with scaling models to very large sizes to do very incredible things, where we can honestly take a step back and glance back and say, okay, we can learn some things about what we've made to date, and which is, we can do really incredible things. But at the same time, why do these things always fail on some of the most simple examples out there? And I think it's just marvelously entertaining, and this is why I really love talking about this paradox. Because I think it's also one of the, I mean, it goes towards this concept of validation verification, right? Because these models don't work in the same way that we perhaps expect them to as humans, right? We can't reason with them or expect them to work or reason the same way that humans do. So we have to basically either change the way that we evaluate them or try to find ways to get across this around this Moravec's paradox, which I don't think will happen. I don't think it's a matter of adding more data to it. I mean, there are concepts like, I mean, talking now from a, I guess, more philosophical perspective, right? But things basically like common sense, right? These are the things where models fail, right? But we as humans can do them, right? Because we have a sort of world model, right, inside of us, right? In a sense, we have this sort of like intuition that despite our best efforts at trying to encode this in data and trying to get the model to learn from this data, we can't really do. I mean, I mean, children learn so quickly, right, in comparison to machine learning models, in the sense that, you really only need to show them a couple of examples of something that they've never seen before, and they can somehow merge that into their world model and can then use it later, right? Whereas for, machine learning, up until, the era of foundation models, we needed a lot of data to be able to train models on new concepts. And now the situation is better with foundation models, but it's not completely solved, right? I mean, there's still quite a bit of a gap. But yes, it's precisely this concept of Moravec's paradox, and particularly as it comes to automotive, it's exactly the reason why I'm completely and deeply unimpressed when I see videos of automated driving systems making very complicated maneuvers and things like this in very heavy traffic, because I know that behind the scenes, that same model has failed to recognize, a stop sign somewhere, or, has, confused a pedestrian for something else, or something like that, right? Something that any child would be able to pick up. So I think it's just something that's embedded in the way that these probabilistic models, are framed from a statistical perspective. I don't think that adding more data is going to solve this.
Wow. On that note, that's that's a very difficult problem. Actually, there's one thing I want you to close this conversation in terms of the thing that really struck me when I heard your first talk was that one of the automotive engineers told you that was we don't always need Swiss Army knife. Sometimes we want a very good steak knife, right? So
Yes.
if you apply that analogy, what would be the very good steak knife in the automotive world, in your opinion?
Yeah, yeah. So in my opinion, the very good steak knife is not just the models that we've had so far inside of automotive that can do very specific things, but nothing else. I would say it's essentially a mixture of these two sort of concepts of an actual Swiss Army knife and an actual very, very dedicated, one task thing like a steak knife. It's actually a mixture of those two. So the way that I sort of see it is you have these very generalist models that are, by definition, by the way that they're even named, these are foundation models. They are the foundation for something that you want to build on top of, right? And that's, what exactly you build on top of. This is the domain specific part, right? That you need to have, that you as a domain expert inside of, for example, automotive, need to build on top of. And for me, what the steak knife really looks like is essentially standing on the shoulders of these generalist models. You use all the data, all the high quality data that you have sitting in your data silo to train something that is a very specific adaptation of this model in such a way that you don't lose the generalist properties. So this model still has an idea of what reasoning looks like, for example, how conversation looks like if we're talking about an LLM, all these things. but at the same time is able to solve very, very specific questions inside of your industry. It's not the frontier AI labs that are going to come up with this, right? Because they don't have access to this data. Yeah. This is on the shoulders of the domain experts, right? It's their job to sort of like push this forward. Automotive engineers and the entire automotive business is just a spectator of what's going on in the AI world. Whereas actually, I think I don't think that's the case. I think there is a very active role that needs to be filled here that nobody else can fill except them. So that's my encouragement and my motivation, is to say, actually, do it.
That's a big responsibility, but certainly needs to be done. Yeah.
I think we have to acknowledge the experience of people who have been working in the field
Yes.
for such a long time, and also the people that, not just the AI field, but also the domain experts that are trying to integrate all this information. Because I think if you're sitting on either side of these views, there's this tendency to oversimplify the other, right? And that's exactly what we can't have, right? Because the solution needs to come from both, right? So the complexities are going to come from both sides, not just from one.
Am I hearing between the lines here that as we move from general uses to domain specific, we really want to change the focus from an autonomous system to a collaborative system that works with the experts and then with the user?
Absolutely. I mean, I think there's no way to get around that, right? So very deep integration between the engineers that are leading this engineering process and the systems that are carrying this out. I mean, a good analogy that I keep in mind, or nowadays, no one that really does any coding has to take a look at the compiler, right, or interpreter of a coding for a particular language, right? No one's looking at that level. Everybody's just looking at the I guess code, which is written in semi-natural language, if you will, right? And if we think about the next iteration of that, the question is, does the code then become what your compiler was 10 years ago, or even just a long time ago, and you move on to the next stage of that and just put complete natural language descriptions of what it is you want to achieve on top, and you just completely forget the code itself, or you just leave this to your agents, right? So I think this is a good example of how things could progress in a sense, but I don't think that we can ever go from 0 automation to 100, right? There's going to have to be some stage in the middle where you interact, where there has to be some sort of interaction for sure. No question about it.
All right. Well, thank you very much, Mauricio, and thanks, Ron.
Yeah, you're welcome.
Participating in the discussion, and we should meet 3 years from now where we are.
Absolutely. This is sort of also my way of thinking when I'm reading all these articles and thinking to myself, I'm going to contact these people in 3 years from now and ask them, like, okay, where are your predictions? How valid were your predictions, right?
Exactly.
So yeah.
All right. Very good. Well, thanks for coming to the show, and we'll speak soon. Okay.
Yeah. Thank you so much. All right.
Okay.
All right, guys.
Bye.
See ya. Bye-bye.
ARM is the industry's highest performing and most power efficient compute platform with unmatched scale that touches 100% of the connected global population. Together with the world's largest computing ecosystem and 22 million software developers, ARM is building the future of AI.